All right, so last block we learned a little bit about rotational kinematics. Today we're going to work on how that motion occurs, and just like with regular kinematics, a force causes an acceleration. In this area of rotational kinematics, a torque causes an acceleration. However, we're not ready to get to accelerating yet. We're going to start with static questions, one where no motion occurs, and then next block we're going to blend the two, kinematics and free body diagrams, and we'll see the dynamics of rotational motion. So we need to start with torque. So torque is simply defined as the tendency to produce a change in rotational motion. Turning now. We don't care if it moves left and right, up and down, in or out. What we care about is, does the object spin? Now, there are three fundamental factors that affect torque: how much force you apply, the direction that you apply it in, and where you apply it. Specifically, where is about how far from the radius. The direction is it should be perpendicular, and the magnitude, of course, is just your strength, how hard you are attempting to twist the object. So if you take a look at the picture on the mid-left here of my equation is force times radius, that's how strong I'm doing it, and how far away from my center of curvature, or my center of rotation. And sine of theta is attempting to tell you that I only care about the perpendicular component. So if you look at the picture right here, what you notice is I have a theta here, but all I care about, the only thing that produces a torque, is the perpendicular component, that which is 90 degrees towards your radius. If you pushed in at the center of radius or out away from the center, such as this component, you're not going to make any spinning occur. So what is torque all about then? Torque is about the perpendicular component of the force. It causes it to spin. If we spin, we know that counterclockwise, of course, is positive, and clockwise, of course, is negative. And again, using that right-hand rule, it's in the z direction or negative z direction. So now, of course, net torque is simply the sum of all your torques, again remembering that clockwise is negative. So let's do an example that actually is not statics, but one that would cause a rotation, though we're not going to really discuss how it rotates. So I have a couple different objects. I've got two beams, okay? One that's 4 meters long on the right, okay, with a 20-meter force pushed on the end. I've got my A, which is my axis of rotation, and then I've got another 8-meter beam that has a weight of 40 newtons placed down the center, and lastly, I have a 30-newton force pushing at 30 degrees to the right. So let's take these forces one at a time. I'm going to take this one first, my 40 newton first, and I'm going to call this torque 1. I'm going to call this over here torque 2. I'm going to call this over here torque 3. Now the mistake most people are going to make with torque is they forget the radius component when we're doing it mathematically. So in this case, torque 1 is 40 newtons, and my radius from the center of rotation is 2 meters. And so my torque, and I'll put newtons here and meters there, is 80 newton meters. Now, this is clockwise or counterclockwise in direction and should be positive. Now, over here, I've got 30 newtons of force at a radius of 8 meters from the center of curvature. And then I have an angle. Now, your angle is always marked off the radial line. So if you extend the line from the radius to your point of your force, you can mark it. Doesn't matter whether you mark here or mark there. They're going to be the same, they're coterminal angles. They will give you the same value of sine and cosine anyways. So I'm going to pick sine of 30. And of course, we know sine of 30 is just 1/2. So 1/2 times 8 is 4, times 30 is 120 newtons. However, this is pushing clockwise, and so conceptually, we need to add a negative in front of it. T2, I can make my sign distinction now, is already negative. I know that. Okay, it's again 20 newtons. Again, it's a radius of 4 meters. My units here. And now I've got to make a discussion on my angle. So there's 30 degrees. I could extend my radius. If you look at this right there, that's also 30 degrees because those are corresponding angles of parallel lines. Okay, so if I got corresponding angles, it's also 30. Again, oh, look at the math. Sine of 30 is a half. Half of 4 is 2. 2 times 20 is negative 40 newtons. So if I do my sum of torques is positive 80 minus a 40 minus a 120. And let's see, negative positive 40, negative 80 Newton meters. And that is the units for torque. If you want to come back up here and put units for torque is a Newton meter. So let's take a look at our next example, one that is going to be in statics. But before we get to jumping to the question, let's talk about what statics mean. Static equilibrium means nothing in the object has either a net force or a net torque. That means we're either not moving or moving with constant speeds, constant rotational speeds or constant translational speeds, or even both. A car moving at 30 meters per second to the right at constant speed, its tires are spinning at constant angular speeds. Our car is moving at constant linear speed, so it is still a static equilibrium question. Now, once I press the gas or press on the brakes, all that static goes away. So how do we do static equilibrium questions? Well, it starts with these three general rules. You start with a free body diagram. You choose whatever point of axis rotation you want. It does not matter because you are not rotating at all. So you can choose the pivot that's best for you. Then you write your free body diagrams and net torque equilibrium equations, and you attempt to solve the scenario. So let's take a look at this picture. I've got two beams or two pivots, A and B, holding up a beam going across the middle. Okay, we're going to neglect the weight of the beam for the moment. We're going to say we got one weight here, 80 newtons hanging down, and I've got another weight on the left of 40 newtons hanging down. So let's draw our free body diagram. So the first force is our forces of gravity. Call straight down. That one's our 40 newton one. Second one there, 80 newtons. And then I also have normal forces, and I'll call this FNB, and I'll call this one FNA. Now, the second trick to static questions is picking the best location for your pivot. So I don't know anything about point A, and I don't know anything about point B. So I'm going to choose one of those two. It doesn't matter. I'm going to go ahead and mark that. I'm going to say this is my pivot for the moment. Okay. So let's do our net force. So our net force equation means that up equals down. So 40 plus 80 better equal FNA plus FNB. So that's a nice easy equation. 120 is FNA plus FNB. You're going to need to get used to systems of equations because that's what's going to happen. Now off to the right, I'm going to write my net torque. Now instead of thinking of it equaling 0, I'm going to say counterclockwise torque equals clockwise torque. So if A is my pivot, let's talk about counterclockwise. The only thing going counterclockwise is my 40 Newton force and my FNB. So my counterclockwise torque, so I'm going to say sum of torque counterclockwise equals the sum of my torques clockwise. So my first torque that's pulling counterclockwise is a 40 Newton of force, and it's pushing at 2 meters plus, so that one's done. Then this guy, FNB, is also pushing counterclockwise. So FNB, don't know what it is, times now his radius is 10 meters. That's my only other counterclockwise. This guy is going clockwise, so I'm going to say he is 80 Newton of force times 7 meters. So that's 80 plus 10 FNB equals, what's that? 8 times 7 is what, 560, I believe? So that's 560 newtons. Okay. So subtract 80. It's 10 FNB equals 480. Divide by 10. FNB is 48 newtons. Now that I have a system, I come back over here. I can say 120 equals FNA plus 48. Subtract 48. And my system is done. FNA is equal to, 72. There you go. So let's do a walk the plank example real quick. So my walk the plank example is very, very simple. So let's imagine I have a plank, and I'm going to tell you that plank is 10 meters long. I'm going to tell you that plank has a total mass of 100 kilograms. Oh, I'm not neglecting the mass now. So I've got two pivot points again, A and B, and I have my plank stretched across the top. Okay, and on this side of the plank, I've got, say, 7 meters. Okay, and on this side of the plank, that must mean I have 3 meters. And I am going to walk the plank this way. And I'm going to say that my mass is 100 kilograms. So what I want to know is at what point will the plank tip over? I'd like you to pause this. I'd like you to try to think about it, and I'd like you to try to answer it. I'll give you a hint. 3 is actually a misleading number. You're not necessarily going to fall off at the end, and you might find out that you just simply fall off altogether. So pause now. All right, so let's take a look at this question. So the first thing you have to know is how to deal with this silly 100 kilogram weight. And I hope you recognize it goes dead center right here at 5 meters in the middle, and that's going to be 1,000 newtons. And so there's 2 meters from the edge. Now, this was meant to be very simple. You also produce a 1,000 Newton force. And so the question is, how far can you walk this way? And the answer, again, is 2 meters. But let's do the work nonetheless. I would say net torque counterclockwise equals net torque clockwise. My weight of my beam is going counterclockwise. So it's 1,000 times 2 equals my unknown force of gravity, 1,000. And that's a big mistake people make. They'll forget mg. It's the weight of gravity times an unknown force or unknown distance d. And of course, you notice that cancels out to 2 meters. Anything beyond that, it would tip over. Anything less than that, you would be fine. Now, if I wanted to know what my F's were at that point, I could do a couple other things to try to figure it out. I know FNA plus FNB equals the 1,000 plus that, and you could try to find exactly how much you have. Now, by the way, and this is an important conceptual understanding, if you have a double pivot, like this at A and B, when you're tipping over, it's the closer pivot that's going to have all the normal force. This FNA equals 0 right there. Okay? And there's my reminder. If an object has a weight, consider it to be all at the center of mass. So that's it for statics. You'll practice another one for homework. But let's move on to something new. So the something new today is that a net force causes an acceleration and translational motion, but we know that your net force is impeded by your mass. What I mean by that is when you have a known net force, the more massive you are, the less acceleration you have. Okay? So it would then make sense that if a system was not in rotational equilibrium, that a net torque causes an angular acceleration and thus rotational motion, but would also be impeded by inertia. Now, that inertia is going to have a new term. That term is called moment of inertia. That term is an I. And so notice the similarities between net torque and net force. Net force, net torque equals not mass, but moment of inertia, not acceleration, but angular acceleration. Moment of inertia and angular acceleration. Now, before we can fully understand this concept, we need to better understand moment of inertia. Now, moment of inertia is very simply defined as a body's tendency to resist angular acceleration. Just like mass is, or inertia is, the object's tendency to resist motion in general. So I need to teach you that it's a little bit more tricky than you expect. So I'd like you to run an experiment real quick. Read this experiment. I'd like you to pause now, read the experiment, go find your two heavy objects. I want you to literally do like a spin around, once with your masses really close to you, once with your masses held out far, and just ask yourself, the mass didn't change, but did the difficulty of spinning change? So I'm going to give you a second. Go ahead and pause now. Try to answer these questions. All right, so now that we're back, I hope you agree that they were not the same difficulty, even though they're the same mass. And what was your reason that it was different? I hope you recognize that when you held the objects really close to your body, that it was very easy, and that when you held the objects real far away, it was really hard. And what I hope you recognize was that the rotational distance between your axis of rotation, the distance when you were swung your arms way out, was much greater than when your arms were close in. The radius was almost 0. And so we have this idea that not only is the moment of inertia defined by how massive the object is, but also of how far that object is away from you. So moment of inertia is defined as the sum of mr squared. Okay? M is the mass of my point charge, r is the distance from that. So what I want you to make sure you understand then is, in order for you to swing or spin as easily as possible, you want the big mass as close to the axis of rotation as possible. The more the massive thing is close to the center, the better it is. Okay? The more massive that thing is farther away from you, the harder it is going to spin. So attempt your conceptual challenge. Hopefully that's relatively straightforward. Give you a moment. If you had to hold this and swing, I guess, a baseball bat as quickly as possible, should you swing from the thin end or should you swing from the fat end? If you don't believe me, go find a baseball bat and try it. And what you're going to find out is that if you swing from the thin end, that it's very hard to spin it around. It seems very, very heavy. You hold the big fat end of your baseball bat and swing it. It seems like it's really, really easy. And that's because when you have the thin end on this side, you have much more mass at the far end that's a long radius away, and so my moment of inertia is very, very large. But when my axis of rotation is on the big end, my mass is very, very close to my center of radius, or center of rotation, and it's very, very easy to spin. So let's do a couple examples. So number one, find the moment of inertia of the above system, rotating about point P. So sum of mr squareds is equal to my moment of inertia. So let's do them one at a time. I've got m1, m2. So m1 is a mass of 3 kilograms at a distance of 4 meters squared. But I'm not done. I also have m2. So plus, that's what sum means, mass of 2 kilograms at 5 meters squared. If you check your limits, you get something interesting. 4 squared is 16. 16 times 3 is what? 48? Something like that? What? 16 times 3. 15 times 3, 45. 48 kilogram meters squared plus, let's see, 25, 50 kilograms meters squared, and we get 98 kilograms meters squared. Pretty straightforward, not too terrible. Let's take a look at one that gets a little bit more interesting. Crazy looking thing. Don't get freaked out. Pick your pivot and do everything. So I'm pivoting about point A first. Okay. I'm pivoting about point A. I'm rotating around point A. It doesn't matter which way I'm rotating. So here we go. Sum, I is my sum of mr squareds. So let's do it one at a time. A, I mean, it's kind of silly, but let's do it. Mass of 3, a radius of 0 squared. Notice, You don't have any inertia when you're at the pivot point. Plus, let's do B. I'm 4 kilograms at 5 meters away squared. Plus, let's do C. 2 kilograms at 3 squared plus 3 kilograms at 3 squared. So, what is that? 0 plus 25 times 4 is 100, plus 9, 18, plus 3, 27. So I believe that's a total of 1, 20, 30, 45 kilograms meters squared. Remember, this is trying to tell, it's just like mass. The more massive this is, the harder it is to spin. So let's erase this. That was number 1 only. Now let's do about a line. This is a little bit trickier. The line BC. So when you rotate about a line, the important idea is that you always pick the shortest distance, the perpendicular distance between a point and that object. So for instance, although you could say point D is 5 meters from the line, it's actually only 3 meters from the line. You pick your perpendicular values. Okay. Now notice B is rotating at the center, so it's not going to have any. Also, C is rotating, so it's going to be 0. But let's just do it nonetheless. So I equals, so let's take a look at this. A is 3 kilograms times 3 meters squared, plus B is 4 kilograms at 0 squared, plus C is 2 kilograms at 0 squared, plus D is 3 kilograms at 3 squared. So 3 to the 3rd power, by the way, is 27. So 27 plus 27 equals 54 kilograms meters squared. Almost done. Let's try a couple more. So let's clear all this junk off, because again, we're going to look at the same picture one more time. So about point C. Okay. So let's speed this up a little bit. So I is going to equal, let's do A. So it's 3 times 3 squared plus B, which is 4 times 4 squared, plus C is 0. I'm not going to write it down anymore. D is 3 times 3 squared. Notice I was trying to help you out a teeny tiny bit. 4 to the 3rd is 64 if you didn't know. This is 27. This is 27. And notice this is just a little bit harder to do than part B. So it's 54 plus 64 is 118 kilograms meters squared, I believe. I'll double check my math. It's not important. The line AD, last one, easiest one at the end. So I'm going to do the line AD. Switch up the colors again. Let's do the line AD. Actually, I want you to try this one on your own. Do AD on your own. Give you a moment. This one's super easy. I hope you recognize the moment of inertia of A is 0. The moment of inertia C is 0. The moment of inertia D is 0. So the only moment of inertia that matters is B. And it is I equals 4 times 4 squared, which again is 4 to the 3rd, or 64 kilograms meters squared. So conceptual challenge, give you a second, try this answer. Which of the 4 examples in this question is the easiest to create an angular acceleration, and why? Well, we know torque equals I alpha. So if I want to maximize alpha, I want to minimize I. It's that simple. Which one has the minimum I? The answer, I believe, is B. So B would be the easiest to spin. It's easier than this one. Surprising, isn't it? This one only had one mass that mattered, but it was still harder to spin because it was farther away. 4 instead of only 3s. Distance is a big piece of this. So now this is the last little bit of something you need to learn. It's pretty cool. It's pretty interesting. Solid objects are 3-dimensional. You can't do it like a discrete point mass. So what I'm going to do instead is I'm going to give you this form, okay? And what this does is it tells you the moment of inertia for different shapes. So the first one is a solid disk, okay? That's pretty straightforward to make sense. Solid cylinder is my second one, okay? It's the same idea, solid disk or cylinder. Hopefully you see the way it's the same. Hollow disk means there's no inside. It's a hoop is the way you kind of think of it. Solid sphere. There's also a... Am I missing the hollow disk? I'll get you the hollow spheres in a bit. Hollow sphere is 4/5 mr squared, but I'll get that one to you guys later. And lastly, the thin rod is 1/12 ml squared. So if I give you one of these shapes and tell you it looks like this, you just need to apply this formula and do it. So again, what is this? These are just known moments of inertia for specific questions. So, what's up? All right, start back up. All right, so the problem is you don't always rotate about the center of the object. By the way, the center of the object is the center of mass because it's a uniformly dense object, so that should be pretty straightforward. Now, there's a second formula that I want to teach you, and that is what happens if instead of, for instance, say I give you a bar here, and I tell you that's my center of mass, so I'm rotating, I'm pivoting about that. What if instead I wanted to pivot about the endpoint over here, some distance d away? The cool thing is you can take your known equation and use what's called the parallel axis theorem, plug in your d value, multiply it by your mass squared, and you get your new moment of inertia for the side. I hope you recognize that if you try to twirl something, it's much easier to do than to spin it from an end. Okay? We'll practice that here with these 4 questions. And then we'll be done for the day. So find the moment of inertia for each of the following. A 5 kilogram uniformly dense rod, 2 meters in length, rotating about the center. So rotating about the center, it's 2 meters long, it's my length, and my mass is 5 kilograms. So I'm going to go back to my equation, look back at your sheet if you need to, and you look up a rod, and you find out that the thin rod's equation for moment of inertia is 1/12 mr squared. And by the way, it's all mr squared, ml squared. Actually, I think it's ml squared technically, but whatever. L squared is the same idea. So 1/12, my mass of 5, my length of 2 squared, that's 4, that's what, 10, 4 20/12ths? And we'll leave it at that. I'm gonna go, I guess you could write 10/6 if you want. We'll leave it as that though, 20/12ths. Oh, a 5 kilogram, sorry about that, uniformly dense rod, 2 meters in length, rotated about an end. So now I'm shifting my rotation. Instead of rotating here like I did in A, so A I rotated there, now I'm moving my center of rotation to an end. So now I'm rotating like this. The whole thing is swinging all the way around. What's important though is that this distance d equals 1 meter. So if I want to find this guy, I'm going to use my parallel axis theorem. My I is the I of the center of mass plus d squared m, or md squared. Ooh, I wrote that wrong. md squared. I apologize. Fix that, please. All right, so I equals I, my center of mass, 20/12ths, plus my d, I moved 1 meter squared, times my mass of 5. So 5 and 20/12ths, who cares? I don't even care about the number. But hopefully you understand the idea of the parallel axis theorem. When you slide from your center of mass, some distance d, you simply have to plug it in. Again, one more time, go back to the top. I apologize. Please fix that to md squared. Don't know what I was thinking there. All right. A solid disk of radius 0.3 meters and mass of 8 kilograms. So a solid disk of radius 0.3. So let's go back to this page. Solid disk, there it is, 1/2 mr squared. So I'm going to write that down. Come back. M equals 1/2 mr squared. So that's going to be 1/2 of m8 of 0.3 squared. Let's see, that's 0.09 times 4. So is that 0.36 kilograms meters squared. Nice and simple. Nice and simple. All right. One universally dense rod of 2 meters in length and mass 20 kilograms is wielded to an welded, whatever, to another rod 4 meters long with a mass of 10 kilograms at the midpoint of each rod. If the rods are then rotated about the weld, wow, I'm having issues right there. Weld, wield, I don't know. What is the moment of inertia? So, bad question, I fixed it. So, a uniformly dense rod is welded to another uniformly dense rod. One is 2 meters in length, So this one's 2 meters in length and 20 kilograms. The other one is 4 meters in length and 10 kilograms. And we're going to rotate. It looks like a fan, kind of a crazy fan, not one that's square. So 10 kilograms. How do we do this? Well, the good news is, just like before, you simply sum your inertias. So my inertia of my first one, and this is a uniformly dense rod again, so it's 1/12 ml squared. So 1/12 times my mass of my first guy was 20 times a length of 2 squared. My second one, I, is 1/12 of ml squared also, but it's 1/12 of 10 times 4 squared. And then what do you simply have to do? You simply add them together. The sum of them. Sum them. Finish it on your own. Shouldn't be too hard. So a solid disc of mass 20 kilograms and radius 0.5 meters has a hoop of mass 10 kilograms and 0.3 meters placed on top of it. So the idea is I have a solid disc. So it's solid. It has a radius equal to 0.5 meters and has a mass equal to 10 kilograms. I then stick on top of it a hoop. So it's hollow, okay, but it has a radius equal to 0.3 meters, centered at the same place, and a mass equal to 10 kilograms. So again, I find each eye individually. So I'm going to say eye of the disc, eye of the hoop, and I simply have to sum them. So let's go back, find your equation for eye of a disc, solid disc. Go back, look at your disc. Disc again, 1/2 mr squared. Hoop, on the other hand, is mr squared. So I'm going to come down here. Last question, eye of a disc, 1/2 mr squared. So let's do our disc. Our disc is 1/2 of 20 times 0.5 squared. That's, let's see, 1/2 squared is 1/4. 1/4 of 20 is 5. 5 divided by 2 is 2.5 kilograms meters squared. Second one, eye of the hoop, mr squared. It's going to be an m of 10, 0.3 squared. So 0.3 squared is 0.09. 10 times 0.09 is 0.9 kilograms meters squared. So what's my sum? 3.4 kilograms meters squared. So you've got two different things we learned today. Static, equilibrium, torque, those go hand in hand, and then this guy known as moment of inertia. You have a homework assignment tonight to try. Ask you a couple basic questions. I do have the answers for those posted for you. And I have two real quick math problems for you to try, one moment of inertia question, and one torque and static equilibrium question. All right, good luck. See you on, I guess that's going to be Wednesday.